So the next topic I want to look at is when we have these enthalpies of reaction, what are some of the relationships, or how do they change if we alter the reaction? Now, we don't necessarily do a lot of these things directly, but it's useful to understand how these values change if we do make changes to the reaction. This gives us a little better understanding of, what they are. And the idea is that they're extensive, right? So they change with the amounts. So if I do anything to alter the equation, it's going to change the value. So I said if I took carbon plus O2 goes to 1 mole of CO2, right? This is just the enthalpy of formation of CO2, right? And it had a value of negative 393.5 kilojoules. But what if I were to double, right? So what if I wanted to know the delta H of reaction if I take 2 moles plus 2 moles to give 2 moles? Well, it's extensive. So since I doubled the coefficients, I'm going to double the amount of enthalpy change. Right? So the enthalpy change for this new equation is going to be negative 787 kilojoules. And so if we alter the coefficients in any way, the enthalpy changes in the same way. So if I triple the coefficients, the enthalpy triples. If I cut the coefficients in half, the enthalpy gets cut in half. Now, another key sort of change is the direction of a chemical process. So I haven't talked about it a whole lot, but if I reverse the reaction, everything about the energetics gets reversed, right? So let's say, for example, our reaction is exothermic. That means the reverse reaction has to be endothermic, right? Because if I do a reaction, let's say, if I do a condensation reaction, so I condense some water. So I go from steam to liquid water. That's an exothermic reaction. The reverse reaction of that would be going from liquid to gas, or evaporation, which is an endothermic process. Right? So the opposite is, the idea is that if I change the direction of a reaction or a change, right, the energy aspects are the opposite. So that, of course, means that the enthalpy sign will change. So the bottom line is here is if I reverse the reaction, the enthalpy value is the same, right? The same amount of energy is still involved, assuming the amounts are the same, but it's in the opposite direction. So if I reverse this reaction and I decompose carbon dioxide back down to its elements, then instead of giving off 393.5 kilojoules, it has to absorb 393.5 kilojoules. So bottom line is if I reverse a reaction, it changes the sign of the delta H. Now, a third relationship is something called Hess's law. And Hess's law simply says that if I have a sum of processes or sum of reactions, I can add those two reactions up to get an overall reaction that the enthalpy change of the overall reaction is going to be the sum of the individual enthalpy changes. So if I have two reactions, 1 and 2, that I add together to give me an overall process 3, then the enthalpy change of 3 is simply the enthalpy change of 1 plus the enthalpy change of 2. So if we look at this, and we look at my overall change here, is going from A plus 2B to 2D, and I can view it as these two reactions where A plus 2B reacts to give you C, right, which involves this enthalpy change, and then C reacts to give you 2D, right, and that involves this enthalpy change. The overall enthalpy change is just the sum of 1 plus 2, right? So it's, the 2 steps equals the 1 overall step. That's basically what Hess's law says. So they're additive, right? If we sum up multiple reactions to get to an overall reaction, the enthalpy of the overall is the sum of the enthalpy of the individual processes. Okay, so let's look at an example here. So here's my overall reaction. Carbon plus water goes to CO plus H2. And I want to calculate the enthalpy value, but I want to do it using these individual reactions. So bottom line is there's a multitude of ways that we can find enthalpy values sometimes. So, if we're sort of thinking about this, right, we've talked about essentially 2 ways so far that we can find enthalpy. We can experimentally find enthalpy, right? This is like calorimetry, right? Coffee cup calorimetry. We can use delta H of formations, right? So this is what we just did, right? We did products minus reactants using my delta H as a formation. Now, Hess's law is really just a 3rd way that we can find the enthalpy of reaction. And we can use simple equations and use them to add up to an overall equation and then add up the enthalpy values in the right way to get to the overall equation. Okay, so let's just work through this. Now, instead of writing this all out, I'm going to go to the next slide, which has it all written out, and then just talk through it for you. Okay, so let's look at these. So this becomes like a puzzle sometimes. And when you see these problems, that's really kind of what it is. We need to take these equations and manipulate them in such a way that it gives us this overall equation. So one way to approach this is to look at what you need to make and what you need to form. So, for example, I need to form 1 mole of CO. So if I look at my equations, I only have one equation that uses CO, right? And that's right here. We're going to do that in blue. So in this case, I have CO plus O2 goes to 2CO. So what's wrong with this equation as written? I can't just use it as written because, first of all, in my equation, I need CO as a product, not a reactant. Well, what do? Well, remember, if we reverse the equation, we can write the equation backwards. And that's going to change the sign of the delta H. Now, I also only need 1 mole of CO, and this reaction has for 2. So if I reverse it and divide the coefficients by 2, I can get to this equation right here, right? Which will help me get to the 1 mole of CO. And how did I get to this value? Well, I took this value, I changed the sign, and I divided it by 2. So now I have CO. Well, what else do we have that we can only find in one equation? Well, we have H2 as a product. But the only reaction that involves H2 is this reaction here. Once we do H2 in green, but notice again, it's a reactant instead of a product, so we're going to need to reverse it. We have 2 moles instead of 1 mole, so we're going to need to divide it by 2. So in order to go from here to here, we reverse the equation, we divide the coefficients by 2, so that means we do the same thing with the delta H. We change the sign, we divide it by 2 to give you positive 241.8. Okay. So now I have CO and price. Okay, well, but these two reactions are fine, except they don't involve carbon, right? So I need to get carbon somehow, and that comes from this reaction here. So I need carbon as a product, or excuse me, as a reactant. Okay, the reaction has carbon as a reactant. I need 1 mole. Oh, it has 1 mole. So I can use this reaction just as is, right? I don't need to do anything to it. So this reaction can stay as is, and notice the enthalpy doesn't change. So now I have my altered reactions that should add up to give me this, so we can check, right? So if I take all of my reactants, so carbon, O2, 1 mole of CO2, another half a mole of oxygen, I'm sorry, just CO2, and water, I have my reactants here. My products, I have 1 mole of CO2, half a mole of oxygen, 1 mole of CO, another half a mole of oxygen, and a mole of H2, and I have all of my products. Now if I do a little manipulation here, where I combine these, I cancel out things that are on both sides. So cancel out 1 mole of CO2 here with 1 mole of CO2 here. I'm going to cancel out 1 mole of oxygen with these 2 half moles of oxygen, and I'm left with carbon plus water goes to CO plus H2, which is my target equation. So it adds up right, so I've done it right. Now it's just simply a matter of adding up the terms. So I got the sum of all of these, add up these numbers, and you get to the delta H of the reaction, 131.3 kilojoules. So by using these 3 equations that I know the delta H is of, I can get to the delta H of this overall reaction using this principle of Hess's law. All right. So that's Hess's law. So I'm just going to end this by doing one more sample equation. I just want to show you one more example of delta H as a formation, because remember in the last slide I said that there's essentially 3 ways that we get to delta H values. Experimentally through calorimetry, coffee cup calorimetry ideas. We get them through delta H as a formation, using the values in the table in the book, doing products minus reactants, and we can use Hess's law. So we just did Hess's law for this reaction. So let's say, okay, what if I just wanted to do this and I wanted to use delta H as a formation? So I've given my reaction, I say, Hess's law, this is fun, but you know, unless it specifically asks me to use Hess's law, this might not be the easiest way to get to the number, especially if I don't know these individual reactions. Can I get to this using delta H as a formation? So here's that reaction. The way that we would do this, of course, would be we would take our products, which would be 1 mole of CO here, 1 mole of H2, and we would minus, so right, these are going to be our products. We have reactants, which are 1 mole of carbon, 1 mole of water, minus the sum of our reactants. And so we're just going to pull in these values. And I'm going to, again, save myself some writing here. I already have this written out. So we're just going to switch to the next slide and walk through it. So if I were to apply this, I would take my one look up in the table, and CO is minus 110.5. Oops. So we got that. plus 0. Right? Remember 0 for the carbon, because it's an element. Or sorry, for the hydrogen. And on our, so we got products minus our reactant. So carbon is of course going to be 0 because it's an element. Water, gas, remember we're getting the gaseous water, that's negative 241.8. So we end up with negative 110.5 minus a minus 241.8 and ends up with positive 131.3. Now, to remind you, they switch back to this slide, positive 131.3 kilojoules. So whether I used Hess's law or used heats of formation, I should, and of course it makes sense, that I should end up with the same enthalpy value for this balanced equation. All right, so this concludes my discussion of Chapter 7. Make sure that you're looking through the study guide, following along on the PowerPoints, doing the homework assignments, watching these videos and any other videos, and make sure you're reaching out with questions